So until now we were looking at solutions where we had made some assumptions about the underlying distribution of different classes. Now what if we don't want to make any assumption about the distributions? Then there is another linear classifier that has a slightly different loss functions, but it works for a wide variety of distributions, and that is the support vector machine. So in support vector machine, the basic idea is the following. So let's say we have x1, x2 plane. And in this x1, x2, we are given some positive points and some negative points. Basically what we are trying to do is we are trying to minimize something called empirical risk. So what is empirical risk? What do we mean by empirical? Empirical is basically the set of points that are given to us. How do we minimize the risk of misclassifying given these points? So here, without going into the original math, basically the basic idea is that we will find a boundary. And now let's say if this is linearly separable, we could have found several different boundaries, right? So we could have also found this boundary or this boundary, but we'll find that boundary, the one that maximizes the margin between the two classes. What is the margin? That we will find those points that are closest to the boundary, okay? And these points that are closest to the boundary, they define some margin from the boundary, and this margin should be maximized. So basically empirical risk minimization is equivalent to margin maximization. Okay, so how do we do margin maximization? We'll come to that in a bit, but now let's look at it a little bit more carefully. If we have a hyperplane that divides the positive side from the negative side and it maximizes the margin between them, any other hyperplane that I have will not maximize the margin, even if it correctly classifies the 2 points. So if I slightly perturb this red line, it will either go closer to one side or the other, or to both sides. So it will not be the margin maximizing hyperplane. So now compare this to perceptron, where we did not have a unique solution as long as we could have a correct classification. Here we will have a unique solution, and that can be shown by showing that this is a convex problem, which we'll come to in a bit. And now here, the other thing to note is that once we have maximized the margin, I can actually have other points that can change the shape of the distribution. So let's say I add more negative points, and I can add it in this shape, this elongated tail. I can add positive points here in this elongated shape. The shapes don't matter. The shapes of the distribution don't matter. What matters is what is close to the boundary. So in that way, this is free from the assumption of the underlying distribution of the shape. It is just trying to minimize the empirical risk by maximizing the margin. So now let's talk about the criteria for what maximizes the margin. Before that, the points have to be on the right side of the dividing hyperplane. So what we want is we want Ti, which is +1 or -1. So Ti belongs to +1 or -1. It's customary to write the -1 first. Okay, and what we are saying is that for every classified point, Ti times, right, W transpose Xi plus B is going to be greater than 0, right? So what does this mean? That for negative points, this W transpose Xi plus B will be less than 0. For positive points, W transpose X plus B is going to be greater than 0, and that we can take care of this sign by multiplying it with Ti. So we are doing the mirror fold along the dividing hyperplane. So now let's subject this to mod of W is equal to 1. Okay, so that we take away that ambiguity. Now once we subject it to mod of W equal to 1, you can see that what we will have is that we want this particular quantity for the points for which it is the minimum. We want this particular quantity to be the maximum. For which points will it be the minimum? The ones that are closest to the hyperplane, the dividing hyperplane, the decision boundary, where this expression is 0, right? So we want to, so basically we have a form of an optimization now. We have arg max W comma B, right, 1 over W bar. So if we don't have mod of W equal to 1, we can have 1 over W bar, 1 over mod of W, minimum over I, okay, Ti times W transpose Xi plus B. Right, so let's unpack this. This is the distance from the hyperplane, okay. This is the mirror folding. So Ti brings the negative points to the positive side, and now this minimum is the set of points that are closest to the hyperplane. All right, then we are normalizing the distance so that the mod of W does not matter. We cannot stretch the distances longer or shorter, and after that we want to maximize it. We want to maximize this normalized distance where mod of W is 1. Okay, if mod of W is not 1, we will divide it by mod of W. So this is one way of solving this problem, and once we solve this problem, we'll get W's and B's that will give us the support vector machine, right? So I'll tell you what is support vector in a bit. The other way of doing this, okay, so here the second way of doing it is saying that either we keep mod of W equal to 1, or the other way is that if we don't keep mod of W equal to 1, we keep the margin equal to 1. Okay, so let me draw this first. So let's say we have a dividing hyperplane. This is a dividing hyperplane. This is the positive margin. This is the negative margin. The positive margin will always be equal to negative margin. Otherwise, we will not have the optimal solution. We can always wiggle the line so that we can go closer to one or the other. So the positive and negative margin will always be equal. So you will have some points, at least one point on the positive side at the margin, and you will have at least one point on the negative side at the margin. Okay. So we will have at least one negative point. Let me change the color again. We'll have at least one point on the boundary, and we'll have at least one point on the boundary on both sides. Okay. So here I need to maximize this margin. Okay, that is basically what this particular optimization is doing. What is this margin? Basically, first I'm taking the minimum distance, minimum sign distance, and then I'm normalizing, and then I'm trying to maximize that. Okay. The other way of doing this is to say that I can stretch this space, all right, and I can in that stretched space the margin will always be 1. So I want to stretch the space around the dividing hyperplane, but I want the margin to be 1. Okay, so here this is subject to, so here I can delete this and say this is subject to mod of W equal to 1. The second way of saying this, doing the same job, is to say I will do the arg min over W and B, right, of mod of W square, okay, such that Ti times W transpose xi plus b is greater than or equal to 1 for all I. That means for all points, this sign distance will be at least 1, and it will be exactly 1 for the points that are on the margin. Okay, for all other points it will be more than 1, but I will stretch the space between the points on the margin by increasing W. Okay, by shrinking W. So why do I want to shrink W? Because if you think about the product or the dot product of W and X, there is an interplay between increasing one and decreasing the other, right? So that if we want to maximize the margin, we want to increase this W transpose xi plus b, but the other way of doing this would be that we want to keep the margin as 1, but by using smaller and smaller weights, which is basically saying that I'm going to try to shrink the space between the two so that the margin remains at 1. So that will be equivalent to maximizing the margin. So here the other thing to note is that now what we have here in mod of W square, minimizing that, is a very clearly convex problem, right? On the other hand, what we have in the constraints, so basically it's a constrained convex problem, or so it falls under the category of quadratic programming. Okay, so to get the solution, we don't simply use gradient descent. What we use is quadratic programming because it is subject to certain constraints, and that constraint is that for all points Ti times this W transpose xi plus b is going to be greater than 1. Now, what happens if the points are not separable? So let's say again we have x1 and x2 plane, and in that x1 and x2 plane we have some positive points and we have a stray negative point that is inside the margin, surrounded by some positive points, but largely it is separated. Can we still find a hyperplane that divides the two? Okay. And how do we basically trade off between trying to get all the points correctly classified, or as many points as possible as correctly classified, and on the other hand maximizing the margin of whatever is closest to the decision boundary? So we want to minimize the empirical risk, but we also want to increase the correct classification rate. So these are sometimes two opposing factors when we are looking at non-linearly separable data. So here what we will do is we will introduce a hyperparameter that will give that trade-off, that will allow us to do that trade-off, and that hyperparameter will be lambda. So we will introduce a trade-off parameter lambda. So this is a trade-off parameter. What will it trade off between? It will trade off between correct classification and maximizing the margin. So it will trade off between sometimes two opposing goals. And how we will do that is we will also introduce something called a slack variable, and this slack variable is going to be for each point I. What is this slack variable? It will basically tell us how far are we on the correct side of the margin, not just the correct side of the hyperplane, but how far are we on the correct side of the margin. So basically it will encode something along the following lines. It will encode a function like this. Let me change a different color. It will encode a function like this, where this is so anything on this side is misclassification, but we also want a margin. So this is the margin. Okay, so it will be 0 when the points are on the correct side of the margin. It will be non-zero or greater than 0 when they are on the wrong side of the margin. When they are misclassified, at that point it will take the value 1, and when they are further away towards the misclassification side, it will be greater than 1. So there will be a range in which it will be between 0 and 1. and that point will be that the points are correctly classified, but they are intruding into the margin. So we have the margin here and we have the margin here. So the points that are going inside the margin, although they are correctly classified, will have this this variable size, slack variable. This is called the slack variable. That will be between 0 and 1. So there are different ranges: 0 for being on the right side of the margin, 0 to 1 on being correctly classified but being on the wrong side of the margin, and greater than 1 when the point is wrongly classified. Okay. So basically what we want to do is we want to minimize over W, B and the entire vector of size, okay, for all the points, lambda times mod of W square plus 1 by n times sum of I is equal to 1 to n of xi i's. Okay, so ideally if it is a linearly separable data, then I can get all the xi i's to be 0. Okay, because I can do correct classification, and I can then minimize. I can find the dividing hyperplane that maximizes the margin by increasing lambda. So if I increase lambda, then what I will get is maximizing the margin, and otherwise if I decrease lambda, then what matters is that I do correct classification. So that is a trade-off between the two. So here one more thing that I forgot to write is there is a constraint here. The constraint is that such that, okay, for all I will have Ti times W transpose Xi plus B, okay, will be greater than or equal to 1 minus xi I, and all xi i's will be greater than or equal to 0. So this is same as saying that I want to minimize over W and B, find the solution by orienting the hyperplane by changing W and B, such that I minimize the following loss function, which is lambda times mod of W square. Okay, and remember the hinge loss that we had, right? So that hinge loss is basically it is 1 by n, okay, sum of I is equal to 1 to n, right? And we will have hinge loss over all the training points, and basically that will be, I will write it as 1 minus Ti W transpose B, sorry, W transpose X, Xi plus B, right, and plus. So what is this plus? Plus means that it is a so if I have some variable, let's say a, right, a plus is equal to max of 0 comma a. That means if only if it is greater than 0, then I will keep it. If it is less than 0, then I will just keep 0. It is also called ReLU, rectified linear unit, ReLU of A. Okay, and its graph, as you can imagine, is on this side. It is its graph is going to be like this, that it is 0 if it is negative, and it is identity when it is positive. Okay, so that is also, so we have incorporated it here in such a way that we are trying to model the following function, right, what we showed earlier. We are trying to model this function, and that is how we have modeled it using the 1 minus that expression in the in the parenthesis above here. Okay, So here what you can see is that there is no loss if we are on the right side with a margin 1. Okay, so here we are holding again the margin 1 as constant and we are minimizing on W. Okay, so now what is this loss function doing? So here we can start to compare different loss functions, right? So if you go back to the idea of a loss function on each point for perceptron, right? So the perceptron loss was like this, that there is no loss when you are correctly classified and there is constant loss when there is a misclassification or negative identity loss when you have misclassification. On the other hand, the SVM is saying that no, let's not just classify correctly, but let's also keep the margin as 1, okay, and shrink W so that the margin is maximized. Right? So that's basically the difference between the two. But these are not the only two choices. We can also have another loss function that will give similar effect to the perceptron. If we have, let's say, quadratic loss on this side and then we have zero loss here, and similarly we can have a quadratic loss here and then a zero loss here. So we can have different ways of modeling the same loss. But what are they actually doing? The loss that we actually want, if we just want to correctly classify, is going to be that we have one loss when we have negative when we on the wrong side of the margin, and we have zero loss when we are on the positive side of the margin. Okay, so what is the x-axis? It's not simply x, it is basically it is Ti times W transpose x plus b, xi plus b. Okay, so that is the x-axis and the y-axis is the loss. Right. So here, this is what we are trying to accomplish, the step function that I have just shown. But that is not the only goal if we want to have some robustness in the classifier. And the robustness comes from maximizing the margin, at least from according to one type of thinking. And how that comes is by shifting this to the right. And the way it is shifted to the right is by using another loss function that is called convex relaxation. Okay, so it's a convex loss function. As you can see, the original yellow loss function, the step function, is not convex, whereas the hinge loss is convex. So this hinge loss is a convex function, and it, or at least a constant times that, is going to be always greater than equal to the loss that we want. And it will also have the property that it will give you, for correct solution, it can give you zero loss. So instead of that, we can have another convex relaxation where the negative on the left hand side of -1, we have a quadratic function, just like I have drawn in the other figure. So there are different possibilities that are there for formulating your loss function, and they all have different behavior. So in some of the exercises, I will have you analyze or at least think through the behavior of different loss functions. On the other hand, when you look at the perceptron loss function, that is not a convex relaxation of the step function, because although it is convex by itself, it is not always greater than the step function. In the range 0 to -1, it is actually smaller than the step function. So it's not a convex relaxation of the step function. The other thing about losses is that if you remember the L1 loss that we had on the weights, right? Here we are talking about L1 loss, not L1 loss, but a hinge loss on this particular term, right? But we had L1 loss on the weights, and because it had a sharp corner, because of the sharp corner in L1 loss on the weights for lasso, we had elimination of certain weights. Here, because we have a sharp corner, in the hinge loss for the SVM, there will be loss of certain points. What are those points? Those are precisely those points that are not the support vector. Okay, so the points that are falling on the right hand side are not the support vector. Only the points that are falling on the left hand side on the slanted line of, so here any point that falls here are going to be support vectors. And the points that are falling on this side are not support vectors, not SV. Okay, so if we go back to our classification diagram, here anything that is, so if we are talking about the negative class, any point that is on the margin, inside the margin, or misclassified, all of them are support vectors, whereas points that are correctly classified and they are away from the margin are not support vectors. So for the soft margin case, the support vectors are not just the points on the margin, they are also those that are intruding into the margin or even are misclassified. So with this we come to the end of the lecture on linear classification. I hope you found it useful, and we will build nonlinear classifiers later on top of these principles for linear classification. Thank you.